Welcome to this master class session titled Prospects for the Mining Industry in Kazakhstan with graduates of Nazarbayev University. We have 4 presentations today within this session, and the first one is by Professor Sergei Sabanov. He is a senior professor in School of Mining and Geoscience who specializes in risk management and mine ventilation. Since we have limited time, I will invite Sergei to please present his talk.
Спасибо большое, профессор Ли.
Thank you very much, Professor Ali, for good afternoon already, distinguished colleagues. Today we are going to have a master class for you. We are going to have 4 presentations, and I'm starting the master class with a topic on potential energy resources of Kazakhstan, and I hope that everyone understands Russian and it will be more convenient. My presentation will be in Russian, while the slides will be in English. I would like to say a couple words. We have started a mini program that includes several courses in this semester, and we invited the specialists from the mining sector to participate in these courses. These are qualification upgrade courses. They comprise, in one semester it is possible to get 3 or 4 courses, and also the next semester. And after the graduation of this micro program of 3 or 4 courses, the certificates are issued. And if you graduate from 3 or 4 programs within our master degree course, you can claim for a diploma of our university. Whereas the difference from ordinary enrollment, you are more independent, and you can physically online participate in the course, and you can choose the courses you are interested or depending on the schedule, and you can distribute them. If you don't have time, you can graduate next year or in a year. It can last endlessly long. It depends on you, and it depends upon how long the university will exist. Usually the course lasts 15 weeks and 3 hours a day, 45 hours per semester. You see my contact details, and you can see it on the slide, or approach me and I'll provide more details. Now my presentation. Almost every professor have several research grants, and we participate in different projects, and we make publication. This is actually our duty. And today I will be about one of the projects that I was developing within the framework of the research grant, and all the students are related to combustible shells of Kazakhstan. Maybe you know what is combustible shells, and I'll tell you briefly. Also, the technologies are now globally used for shale processing to shale oil that requires a refinery. Even gasoline is possible to produce, and the method for assessment, and you see the map and the deposit of oil shales that we managed to identify on the sources which are available. If you are interested, the companies may address to geologists and to get the reports. But now it is just a preliminary conceptual assessment. On the slide you see certain deposits on which we have more or less adequate information. At the table you see the characteristics of the deposit. In the upper part of the table you see deposit Kinderlich, and it has several layers, its characteristics, millions of tons, and all oil shale tones which can be recovered, and calorific value. You can burn it only just for electricity at power plant, or you can extract oil shale. And now talk about the technology. And the table also shows the depths of these deposits, their thickness, moisture content, and other possible useful information. How much sulfur, carbon, or ashes contained. These are important specifications for the project. And with the stars, you see the reserves that have been assessed on A, B, and C1 categories, which in international standards can be considered as measured and indicated reserves. So they can be a basis for use, while the others are the figures that would require double check and further investigation and geologically explored. On this slide, you see the technologies of oil shale retorting. These technologies exist all over the globe, and they are not numerous. As at the industrial level, only China, Estonia, and Brazil are developing this oil shale, while other countries are not using these industrial scales. And that is why these retorts that extract shale oil are now in a pilot level. The one to which we can trust is in China and Estonia. And also this information can provide us an idea on yield of the oil. These are the technologies that gives us reliable interval of the oil yield. If it is not an industrial installation, and when we move from pilot installation to industrial, this value can be worsened. What is retorting? It is slow heating with a temperature of 40 to 50 to 500 degrees. The slow heating of shale. First gas evaporates, and then light fraction, and then shale oil. And then semi-coke is created. In the power plant, the temperature could be 1200, and the fuel will be burned immediately, and the steam will rotate the turbine, and actually ash will also remain. Do you remember in the beginning I have shown ash content? Those were the technologies that we discussed. What we need to assess ore reserves which are prepared for recovery, and where we can get the final product. For this we have to understand the recovery rate, the percentage broken down by the processing technologies. And we also use this methodology. So why it is a combined methodology? First is for petroleum, which is used to identify the resources. And another technology methodology is used for mineral resources, because shale is a hard component. It is recovered rock, but on one hand it can be used for electricity production, just to burn it, and on the other hand it can be used as a shale oil. Here we have to establish a methodology that could be acceptable for the resource estimation. And now you see a triangle diagram that demonstrates the steps. The first one, we are looking at certain formations of oil shale which have a potential, and then we are increasing the level of confidence to understand to which extent they are explored and whether they are well explored. And then we are moving to shale oil production, and it may happen that shale oil is not a final product. In Estonia, they are used as additives to diesel fuel so as the freezing temperature be decreased. So it is a wide spectrum of chemical production. Even a nail polish have other types of products can be produced of shale oil. From the methodology, we managed to create, using a regressive analysis, a ratio of correlation between shale oil and a calorific value. In the field diagram with the blue spots, you see it on the left. And if some project, as you have seen in the first table, was assessed only on calorific value, we can create a correlation of the shale oil yield. This is done based on a number of explored deposits all of the world. And here you see the probability tree and what steps can we do on some inferred reserves. Then we move to identified resources, and then we add the oil content, and that's the recovery of mining rocks, and recovery of retorts. As an example, I would like to take a Kendrick formation, and here you see we have used Monte Carlo simulation. You have a range from 4 to 9 in this schedule that gives us an understanding of potential oil content, because this deposit has not passed through detailed exploration, as Monte Carlo simulation provided only with range. As the level of confidentiality is low, we provide only 50% of confidentiality. Here you see a more detailed probability tree. We are moving from 700 million that people believe that they are present here, and we are moving up, and the upper, the red color, it proves that it is more reliable, but in total there were only 20 million tons in category of ABC1 resources, and out of this 20 million, we see how much have been lost in mining. We remove these losses, and then we see the range on recovery. And as a result, we get only potential 1.2 million tons of reserves. We can call them reserves as for these certain steps have to be done in the researches and feasibility study. And you see the range on distribution by Monte Carlo. We demonstrate here two different technologies, a conventional one, collector that has been tested in industrial scale, and the pilots. We show the range to the investor to understand how much can be recovered. This is how Monte Carlo help us to identify, because all of these are uncertainties require an additional study. So what the methodology studied, what is included, how much tons of mineral resources, oil grade or recoverability in mining operation, or losses, or recoverability if we use retardant technologies. So that's what I would like to present, as we are very much limited in time, and I would like to invite our next speaker, Professor Ali Martazali.
Everyone, and welcome to my presentation titled Investigation of CO2 Storage in Subsurface Geological Formations and Depleted Underground Mines. This is a brief outline, project overview and significance, research team that we've put together, and the proposed research programs, followed by publications that we've produced so far. The significance of the project, as you know, carbon dioxide capture and storage is the process of collecting CO2 and injecting into subsurface geological formations to isolate CO2 from the atmosphere. The focus of this project is the geomechanical design aspects of CO2 storage in subsurface. To safely store carbon dioxide, it is vital to ensure the integrity of the caprock during the CO2 injection process, and the reactivation of major faults and discontinuities is a major caprock breach mechanisms. We have divided these topics into two major research streams. The first one, investigation of fault activation mechanism in carbon storage. It is an ongoing research project. We have done significant improvements on the topic, and the second stream, which is in line with the theme of this conference, is investigation of CO2 storage in depleted underground mines, including 3D simulation of a typical underground mine main developments, and looking into the dynamics of CO2 injection into these major development structures, analytical, numerical, and experimental studies of CO2 penetration and interactions with backfill material and backfill stopes, and a geomechanical stability and integrity analysis of a caprock, underground mine host rock, and major development structures. I'll go through some of the works that we've done before and what we intend to do for future research. This is a research team for now. The research team that we have, one PhD student and 3 master students are working on the subjects, and new students will join the project later on. This is the whole concept, what it is, the problem. This is, as you see, a CO2 plume at the bottom, CO2 injection location, and different geological layers, and those major discontinuities or faults. They provide a path for the CO2 to leak to the surface under pressurization levels. What we intend to do is to look into the possibility of the CO2 leakage from faults, major geological structures, and try to develop a shear strength model for these faults, and look into change in fault permeability as a function of sleep, confining stress, temperatures, fault gauge material composition and distribution. This is an ongoing project. We've also looked at the effect of fault geometric properties on the possibility of CO2 leakage. This is what it is. It basically is an actual fault gauge material, the same scenario. So there are limited data on this material, and the first step, we try to build some artificial samples of fault gauge material and test them in the laboratory, and prepare some samples. As you could see, 14 centimeter by 4 diameter representative fault gauge material sample. We inserted the sample into our core flooding system at SMG and looked into the effect of confining pressure on change in permeability. These are some preliminary results that we have obtained so far. This is an ongoing experimental program as part of a PhD thesis. On the numerical side, we have done comprehensive 2-dimensional, 3-dimensional using finite element and distinct element numerical modeling. The 2D modeling is already finished. We've used RS2 finite element code to look into the effect of caprock deformation and breach mechanism. On the 3D modeling, we use distinct element method to look into the geometric effect of faults. This is a summary of 2D modeling. You'll see the list of publication and can find detailed information on what we've done. On the 3D modeling, once again, we took a full-scale model of Insala storage site in Algeria. As you see, the dimension of the model, 3 kilometer by 2 by 2 kilometer, and a major fault intersecting the injection zone. This is a comprehensive parametric study that we've done 23 separate 3D analysis looking into the effect of different parameters, just to give you an idea of what we've done. This is some results that we have produced so far. It's an interesting on the mechanics of fault movements under CO2 storage condition. Once again, the papers already published in 2 intersecting faults. So this is what we've done so far, and still working on it. But the topic that we think in line with the theme of this conference, and we would like to work with the mining industry, is basically the potential for injection of CO2 to depleted underground mines. Three major research areas, including 3D simulation of a typical underground mine main development, and looking into the dynamics of CO2 injection and flow into the major development structures, analytical, numerical, and experimental studies of CO2 penetration interactions with backfill material and backfill stopes, and geomechanical stability integrity analysis of the host rock are the topics to be delved into in these new topics. This is a typical underground mine development structure for two of the most famous underground mines in Canada, Creighton Mine in Sudbury and Hoyle Ponds in Timmins, Ontario. As you could see, the depths, they're working at 2.5 kilometers and more, so significant volume of development structures that once the mine is finished, depleted, provides a great amount of space to store, inject CO2 and keep it incarcerated there for longer period of time. So this is an interesting topic with regard to the deep mining, underground mining industry. It is Kazakhstan. Some of them are toward depletion, and there is a great potential. It's an industrial sector to inject the emitted CO2 into these underground structures and use that empty space. This is another layout plan view of the development structures in an underground mine in Canada. As you could see, some backfill area, mining area, which are backfilled, and then the development structures, which are huge space, average dimension 7 meter by width by 6.5 meter height tunnels. They are well supported. They have been served for like 30, 40, 50 years, the life of the mine, and then they once the mine is depleted, they're available for injecting CO2 in a significant volume. So this is those topics, just review I just mentioned. So this is examples of major development structures, including ventilation shaft, access shafts, incline, the main access tunnel, inter-level ramps. You know, they are developed structure, well supported, served during the life of the mine, and once the mining is finished, they are available as empty spaces to be used for CO2 storage. Just to give you an idea of how much space we are looking at, just one example for a typical underground mine at the depths of 1,000 to 2,000 meters. Main access volume, you're looking at 250,000 cubic meter, haulage and main drifts, ore passes and ventilation raises. These are major development structure with significant volume, and at the end, if you sum up them, you're looking into 600,000 to 2 million cubic meters of space available for CO2 storage. This is for typical stoping mining methods. For other mining techniques such as block caving, panel caving, obviously this space is much larger. And assuming a 2 million cubic meters of underground mine cavity at deep pressure could store approximately 1.4 million tons of CO2 in supercritical form, assuming proper sealing and pressure outlines. So once again, so this is the goal, basically, to simulate a typical underground mine and look into the dynamics of CO2 injection and interaction with these major structures. What we intend to do is build a 3D model of the main development structures of a depleted underground mine, use computational tools to enable the simulation of the fluid flow, simulate the internal pressurization of CO2 injection cycles on main mine openings and development structures, considering boundary conditions and mechanical stress field of the underground mine host rock. Evaluate the equilibrium state of the main entrance points of the mine, such as shafts, and make sure that there is enough like strengths there at those interfaces to prevent CO2 leakage, and evaluate the potentials of CO2 leakage from those injection points. Evaluate the potential of large leakage from major geological structures such as faults and structures. In terms of analytical, numerical, and experimental studies of this CO2 penetration interactions, obviously backfill is one of the most commonly used support system in underground mining. In advanced mining countries such as Canada, USA, South Africa, Australia, cemented paste backfill is a common support system. Portland cement is the major type of binder used in the mining industry for cemented paste backfill, about 2.5%. The cost is significant. In Canada, annually, they're spending $75 million on just the use of Portland cement as a binder in their backfill preparation. So binder composition is the most expensive in common in preparation of CBE. One way to reduce the binder consumption of cemented backfill while maintaining the overall strength and deformability is to incorporate carbon dioxide into the cemented paste backfill during its preparation. It is beneficial to experimentally investigate the influence of carbonation on the mechanical and strength parameters of cemented paste backfill and cost saving arising from the reduced binder use. And obviously enhancing mine backfill technology is intended to lessen the mining industry's greenhouse footprint. So this is just some more thoughts on the same topic. I'll skip. This is just a snapshot. This is an AI-generated diagram of what we intend to do at an experimental level. Do some experimentation, just creates 1 by 1 by 1 meter or larger representative samples of backfill material, inject CO2 in it under different conditions, and look into the effect of CO2 injected backfill material and characterize this material under CO2 injection condition. In terms of geomechanical stability, once again, this is a physical model of a backfill stope. You see a gap at the top. There's a significant volume there. Also, there is permeability of the backfill that has potential for CO2 injection and storage. This is a typical free diagram of backfill usage in underground mining. And once again, in this final phase of this research, which is geomechanical stability and integrity analysis of the backfill underground mines, we intend to build a 3D geomechanical modeling of backfill-supported mining methods, a full stress analysis of mined out areas and surrounding host rock, explicit consideration of major geological structures into the 3D model, modeling of backfill mechanical behavior under in situ condition, simulating the effects of CO2 injection into backfill stopes, looking at effects of backfill gaps at the top of this stope, effects of CO2 injection on backfill mechanical strength properties, interaction of CO2 with the surrounding host rock, effect of CO2 injected backfill stopes on a mine scale stress field, study of the behavior of the major geological structures such as faults or shear zone, and at the end, evaluation of CO2 breach mechanisms from main development structures are also geological. As you can do at the right side, so it's a huge underground mine, huge space under, and huge potential to capture CO2. Some of the publications that we have produced so far, you can look into and collect more information if you want. So that's the subject. We hope we can establish some ties with the industry and get some funding support. This is sort of a national project, and it is beneficial for the whole country, to all, mainly mining industry, like the whole community, in terms of reducing the CO2 emission footprint and controlling it. So that's the end of my presentation. If you have any question, we'll be happy to. Thank you very much. Thank you.
Okay, so hello everybody. Today we're going to discuss use of water in mining industry in Kazakhstan and share some findings of a research that was done by faculty and master students at the mining engineering program, Nazarbayev University. So let's begin our discussion by first considering the level of production that various extractive industries in Kazakhstan have experienced, have delivered since year 2000. So as you can see, the production levels of all minerals and crude oil have been growing steadily, but especially striking is the increase in copper ore production since 2015. It really stands out. So this is a historic data, and as you are all aware of, given the mining potential of Kazakhstan and the significant investment that's happening right now, we can expect even more rapid increase in the level of mining of various minerals in the future. So this is great news, of course, because mining creates new job opportunities. It creates significant tax revenue for the government. However, at the same time, mining is known to produce very significant and long-term environmental impacts. So why do we care specifically about the use of water in mining? Water is essential for the use in mineral processing and storage of mining waste. In established mineral producing countries, water use in mining accounts for 2-4% of the overall water use at the national level. However, at the regional level, the consumption of water by mining is considerably more than that, and may lead to conflicts with other water users, not just because of the impacts of mining on the availability of water for other users, but also because of the current and long-term impacts of mining activities on water quality. For example, in the United States, currently there are around 500,000 historical mines that continue producing environmental impacts and require significant public funding for their remediation. A lot of those mines are producing acid mine drainage and result in continuous contamination decades after such mining activities have stopped. So as a result, as Kazakhstan is approaching or maybe already experiencing mining boom, it is very important for us to learn from this experience and already start taking preventive measures to avoid negative impacts of mining on water resources. So, of course, leading mining companies have been actively managing and optimizing their water use. So the main direction was to decrease water intensity of mining activities, improve management of water flows, recycle, reuse water used in their operations, and improve the quality of their discharge. In order to be able to track whether such activities actually result in anything, it is very important to monitor and gather data on water use in mining. Some major mining jurisdictions, such as Canada, have been collecting data on mining use at a highly disaggregated level, and you can find information on how much water was used, recycled, and discharged by coal mining, iron ore mining, actually by metal mining and industrial mining since 1980s in Canada. But however, at the same time, the industry itself has been actively working on developing reporting standards that would apply to specific companies and actual mine sites. So companies have been disclosing this information following international on so the key standard nowadays is the one developed by the International Council for Mining and Metals on water disclosure. So these guidelines are based on the water balance approach, where all withdrawals have to equal to consumption and discharge. And the key point here is a very holistic definition of each of these items. For example, withdrawals include not just surface water withdrawal from, let's say, rivers or lakes, but they include even withdrawals of water from precipitation and runoff. And for example, discharge also includes not kind of just obvious discharge into the surface water bodies, but, for example, seepage from the tailing storage facility. And the key focus of these recommendations is also to track these various water flows according to their quality, because fundamentally the priority for mining is not only to decrease the amount of water that they use, but give priority to low quality usage. So let's see what can we learn about about water use in mining in Kazakhstan. In fact, there is not a lot of data at the industry level. However, even the one that we can deduce from the available data shows that on the one hand, we see reducing levels of water consumption in the entire extractive industries in Kazakhstan, which initially seemed to be like a very good news, because as you see at the bottom of the diagram, that withdrawals from the surface water bodies stayed relatively constant until year 2015. However, since year 2015, you see that water use has, water withdrawals have increased very rapidly. And in fact, right now, since year 2000, all of the water that mining extractive industries use represent withdrawals from surface water. And surface water is considered high quality water. So it basically implies very low levels of recirculation and low level of low quality usage in mining. So because there is very little information on water use at the industry level, what we have done, we've done a detailed case study of water use at a specific mine. So we used the ICMM approach and methodology and did very meticulous tracking of all flows of water into the mine site. And we have gathered the information that we can now compare to how much water and in each ways it was used in similar operations in other countries. So our comparators produce the same product as the mine that we're analyzing here. So as you can see from this table, our Kazakhstani mine that we analyze relies much more heavily on surface water withdrawal, which is considered high quality withdrawal. At the same time, we see that the company and this particular site has zero withdrawals. It has zero discharge, unlike international comparators that discharge around 30% of all the water that they consume, and a significant portion of which is high quality. So the reason why this company doesn't have much discharge is because most of the water that they use is then recirculated, which is good, but a significant portion, 60% of the consumption ends up in waste. So in comparison to other companies, this is a fairly high indicator. So combining all of this, we are not surprised to see that water intensity of this operation is very high compared to international comparators. And the reason for that is, on the one hand, is basically lack of withdrawals, and also reliance on high quality water source is quite untypical. So what else did we learn about from this case? So we found out that this company is growing very rapidly in terms of this output level. Its ore processing quantity grew at 6% per year over several years. We use data over several years. At the same time, operational use of water was growing almost at the same rate. And also, pay attention, it's really striking that water withdrawals from surface water bodies grew at 10% per year, and amount of waste grew at 11% per year. So this is really high rates of growth. If we expect that other mines operate in the same way, and all of them jointly increase their water withdrawals from surface body at 10%, this is going to be a very significant impact of mining on the overall water availability and its quality. So why did this happen? So we found out that, first of all, this company was allowed by the government water permit to withdraw 30% more than actually it needed. So it means that the government is not putting any constraint to incentivize water saving within this company or mining companies in general. And not only that, the tariffs, the fees that the company pays for water in general in Kazakhstan are considerably lower than international prices. So something around 10% of the average international price for water is the current water price in Kazakhstan. And the our explanation for why the company is not discharging any water, not returning any water that is using back to the environment, is because in our country, regulations on the quality of discharge are very underdeveloped. They are standards for the quality of effluent of discharge are determined on a case-by-case basis from discussions, from negotiations with the government, which is extremely atypical, not usual for mining jurisdictions. In mining jurisdictions, such as in Canada, the quality of the effluent, the quality of the discharge is the same for all, for example, metal mining companies. As a result, this regulation is highly transparent, and the regulatory risk for mining companies as a result is not as high as compared in Kazakhstan, where such effluent quality regulations have to be negotiated with the government. So basically it means that there's a lot of work that the Kazakhstan's government has to still do in order to align their regulations with respect to water use in mining with the best practices that have been established, that have been achieved elsewhere. So basically, what is our conclusion? Fundamentally, here in Kazakhstan, we are just facing the beginning of the mining boom, and we don't want to have mining contribute to the difficulties with respect to water access that are already existing in our country. In our country, there is already medium-high level of water stress, similar to the one that exists in the United States or in China. So not only that, also our country is the largest landlocked country, and all the rivers that we have in the country either originate abroad or they flow to foreign countries. And any issues related to water contamination, the decrease in the availability of water may have international implications. So we have to be very careful about that. So, of course, at the level of the mining companies, there's a lot that could be done, a lot of the technologies that are already existing. Fundamentally, the mining companies should prioritize use of low-quality water, and to do so, the government has to provide the proper regulatory framework to give such incentives for the mining companies to adopt more water-saving types of technologies and managerial approaches. So, this has been just a very short snapshot of the research that we have done, both on Kazakhstan and on Canada, on water use, so you are more than welcome to learn more about it. But basically, this research demonstrates that policymakers in Kazakhstan need to do a lot of work in order to make sure that the mining production in Kazakhstan doesn't result in long-term and in sometimes irreversible impact on the environment. There is a lot that the policymakers have to learn about mining, and I would like to add to the words of my colleague, Professor Sabanov, who invited the mining company representatives maybe to consider doing some professional development courses at our university. I think such professional courses will be especially valuable for the policymakers. So please, if any of you are from the government sector, from the NGOs, from consulting companies, you are also more than welcome to take such courses from our program. Thank you very much.
All right. So, thank you so much, Professor Zavrish. That was real great. Thanks for that. So, we'll follow up with a presentation about the oil and gas industry, even though it's not about like mining, but we intentionally selected these areas because it's more, we would like to demonstrate that at any point of the planet, we can really measure the points with a millimeter scale of the precision. So, I'm Dr. Emil Bayram from Nazarbayev University. It's over 5 years. I joined the academic and research activities after 25 years in the marine and onshore oil and gas career in Azerbaijan, Georgia, Turkey region. In this presentation, we'll shortly review 3 case studies, focus on the surface deformation risk assessment for the oil fields and pipelines located around the Caspian Sea. The first one is a Tengiz oil field, the second one is a Kashagan oil field, and further on we'll shortly follow up with the pipelines. Right, just for information for those who are not from remote sensing field from satellite technologies, there are radar and optical satellites. The difference is that radar is active and emits pulses and measure the backscattering properties, whereas optical measure the reflection of sunlight as a passive satellite. In the current studies, we employ the radar satellite missions because it has the capability to monitor ground deformations. So we use a non-standard approach. We use a deep learning to detect the well paths before running the interferometry on the Tengiz oil field. So we observed the Tengiz oil field from 3 satellite missions, and as you can see here, those are Sentinel-1 from European Space Agency, Cosmos Skymet from Italy, and TerraSAR-X from Germany. Observations were selected because of 2 reasons. The first one is the achievement of actual vertical and horizontal displacements, since it's only possible using observations from ascending and descending satellite tracks. The second one was related with the absence of any geodetic measurements. Since we cannot enter that terminal, then we can really monitor that from the satellite missions. And using 3 satellite missions allowed us kind of a cross-validate and verify the precision of our measurements. And as I mentioned, we use an advanced deep learning approach to detect the well paths so that we can really target our interferometry to those well paths rather than running that for the whole satellite image, because that would take like several months of the processing that we reduced to 3 days of processing. So we ultimately detected 159 well paths out of 174 well paths. As a result of the interferometry, we could measure vertical deformation velocity in terms of the subsidence and uplifts. From all 3 satellites, we could observe similar spatial patterns indicated as reddish-yellow for subsidence and greenish-blue color for uplifts. Red well paths are those subject to significant subsidence, with annual subsidence velocity of minus 54 millimeter. However, we should also consider areas subject to uplifts, indicate as a greenish-blue color. Similar approach could be huge optimization, simplification, and cost reduction for oil and gas industry. In the prioritization of site risk assessment, in the inspection activities, knowing in advance subsiding and uplift well paths vulnerable to damages. Moreover, remote satellite measurements are safe because of no human intervention by site visual inspection activities. Similar process of ground deformation might be directly related with the spatial distribution of oil extraction and injection activities. In a different study, we observed the vertical and horizontal eastward and westward deformations, and also northward and southward deformations. The interesting phenomena here that this area is crossed by faults, detected patterns of the subsidence and horizontal movements are spatially located between those faults. This means that these deformations are also caused by the tectonic processes. Moreover, we could observe some water accumulation patterns in the subsidence area, subsiding area, making that more vulnerable to the subduction process through the impact of soil cover and groundwater level. So which are the benefits? The benefit of the present study for the oil and gas operators might not only be focused for the risk assessment and prioritization of inspection activities, but could also play a significant role for better understanding of oil and gas reservoir behavior in the process of planning of production injection activities and enhanced oil recovery to maintain pressure of oil productivity. So one by one, simple, low cost and optimized monitoring and prioritization of site inspection activities by initial risk assessment, definition of geodetic geotechnical geohazards compliance standards to determine what should be considered as a risk, to consider further investment activities for mitigation measures. So here we can really determine whether or not the operator should invest any cost if the subsidence really valuable of that to be invested for. Better understanding of reservoir dynamical behavior, that's one of the key interventions for that. Significant cost and timing reduction and strengthened safety factor. Prediction of ongoing subduction and uplift processes. Quality assurance of in situ geodetic and topographic surveying. Better understanding of natural processes like tectonics and hydrology. Current approach that we use through deep learning also allowed us to optimize to reduce the timing from 3 months to kind of 3 days, Combination of different satellite missions to achieve millimeter scale of precision across foundation with geodetic surveying. So as I said, at any point of the planet, we can really detect the millimeter scale precision of the deformation. It's necessary to mention and emphasize that it's complicated to get similar broad picture observations using standard geodetic point-based measurements. Moreover, geodetic surveying is quite costly and missing historical observations most of the time. Provision of actual and horizontal measurements are crucial since line of sight from the direction of the satellite might be misleading of the oil and gas operators. Basically, when you would like to make some action on the ground, the oil and gas operator, they ask with the precision to show where they do have to make any inspection activities with the high precision of the coordinates from GPS. Right. Another study is focused on the Kazakhstan oil field that was monitored from Sentinel-1 and Cosmos SkyMed images. The use of interferometry technology was decided based on the fact that the oil infrastructure is built on the artificial island. Since standard platform is more vulnerable to regular oscillations, which could create more complications and misleading results for interferometric measurements. It's well known that Kazakhstan oil field is operated under weather conditions, complicated weather conditions, in terms of the sea ice during winter season, temperature variations, wind speed, and currents. As a result, we could observe spatial patterns of subsidence in the northern and southern areas of oil field with annual velocity of -4 millimeter a year. So you can see even here, we detected up to millimeters of the scale of the deformation. Our measurements from both satellites showed a good agreement. Area 1 and Area 2 installed on the piles were identified to be the most subsiding areas based on the identified spatial patterns from interferometric measurements. And the last one, and I'm finishing. If you pay attention at this, this is a initial section of Baku-Tbilisi-Ceyhan pipelines, and it's located in the pretty active area that's crossed by the seismic faults. So our measurements showed the primary ground deformation processes occurring between those faults rather than on them. So if you bring the standard geological approach, if you bring a standard geologist, he would actually mention that you need to install the GPS station right on the faults. But this would be misleading, and it would be really cost-consuming process unless you know where the subsidence is really occurring. However, without similar broad observation, standard geological and geotechnical approach could be misleading in the planning of the inspections. Interferometry plays a significant role in the process of planning and justification of needed investment for geohazard risk mitigations. So as you can see on that picture, the blue spot of the subsidence occurs right between those faults, not on those faults. That's the way how we can say where the pipelines they have a risk. So we selected the most simple example. We've got a lot of experience working for mining, using the same technology for mining, but in this case we selected the petroleum to make a simplicity for the comprehension. And the technology here that the subsidence might be like in the oil and gas might be up to 50 millimeters, 60 millimeters, but in the mining that would be up to more than 1 meter, more than 10 meters in the specifically in the underground mining. And in that case, we use a different approach of the data analysis, looking at the decorrelation between the satellite data to understand which areas are mostly decorrelating to understand the most subsiding patterns. Thank you so much for your attention.